Similar to alkenes, alkynes also react via electrophilic addition reactions. And if we have alkynes, then the triple bond acts as nucleophile, and the reaction mechanism is very similar to that we just discussed for alkenes. So let's start with the addition of hydrogen halides to alkynes. Alkynes react with hydrogen halides in a two-step reaction to produce halogenoalkenes, which are also called vinyl halides. The reaction mechanism for this addition reaction is exactly the same as we discussed for the alkenes. Hydrogen halides add selectively to unsymmetrical alkynes to form the more substituted halogenoalkene, which is predicted by the Markovnikov rule. And the reason for this is that the addition of the proton to the carbon-carbon triple bond selectively forms the more stable vinyl cation, so a secondary vinyl cation instead of a primary one. And if we have a brief look on the reaction mechanism, you already know this. So what is different is just that we do not have a carbon-carbon double bond here. Now we have a carbon-carbon triple bond. But all other reaction steps are exactly the same. So in the first step, which is the slower one, we then produce the intermediate vinyl cation, which is a secondary vinyl cation, because this is more stable. And then in the second step, we have the attack of the halide ion, and then we end up with this halogenoalkene. And important here is that based on the Markovnikov rule, we have the halide always at the higher substituted carbon. So this is a way how we can produce halogenoalkenes regioselectively. And what is also important is to see that if we add two equivalents of hydrogen halides, this will lead to the formation of geminal dihalogenoalkane. And geminal means that both halogen atoms are at the same carbon atom. So, and if we now compare the addition of hydrogen halides to a carbon-carbon double bond and a carbon-carbon triple bond, then it might be surprising for you that the addition to a carbon-carbon triple bond is slower than the addition to a carbon-carbon double bond. Also, we know that a carbon-carbon triple bond is more electron-rich compared to the carbon-carbon double bond. So, and now you might wonder, why is this the case? And to answer this question, we have a closer look on the stability of the vinyl and the alkyl cation. So the vinyl cation is the intermediate if we have a carbon-carbon triple bond, and the alkyl cation is the intermediate if we have carbon-carbon double bond. So, and the vinyl cation is less stable than a similarly substituted alkyl cation. Hence, the Gibbs energy of activation for its formation is higher, and therefore it will be formed slower. So this already explains then why the addition of hydrogen halides to a carbon-carbon triple bond is slower than the addition towards a carbon-carbon double bond. And now we need to understand, why is the vinyl cation less stable than a similarly substituted alkyl cation. And we can explain this difference with the different electronic effects between an alkylidene or an alkyl group. The alkylidene group here has a stronger electron withdrawing effect compared to this alkyl group here. And this in turn means that if we have an alkylidene group, this positive charge is not as good stabilized as for this alkyl group with less with electron withdrawing effect. And this then finally explains the differences between the addition to a carbon-carbon triple bond and to a carbon-carbon double bond. In order to synthesize aldehydes or ketones out of alkynes, it is necessary to add borane to the carbon-carbon triple bond and subsequently perform an oxidation reaction. And here it is important to remember a terminal alkyne yields an aldehyde, while an internal alkyne yields a ketone. So now we will have a closer look on the four-step reaction of a terminal alkyne towards an aldehyde. And this reaction can also be described as hydroboration followed by oxidation. So let's start. Here is the first step. It is a syn addition in order to produce the vinyl borane. And then we do this hydroboration 2 more times in order to finally produce a trivinyl borane. And then the third step is the production of an enol. And enol means that the hydroxide group is directly attached to a carbon-carbon double bond. And the fourth and last step is the tautomerism. It is the equilibrium between the enol and aldehyde. And as you can see here from the different length of the arrows, the aldehyde is thermodynamically preferred. So, and how can we explain this tautomerism? The hydrogen of this hydroxide group moves towards the carbon atom, and then the double bond, of course, moves in position in this molecule as well. That's why we have this tautomerism between this enol and the aldehyde. And if we start with an internal alkene, then we will not produce the aldehyde, but then instead we will produce ketones.